Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is an Inveractive problem. The problem appeared in October Cook Off and has a difficulty level of easy medium. The prerequisites for this problem are binary search. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the detailed approach to the solution to the problem, followed by which we will be seeing the pseudo code and then quickly going through the C++ code for the same. The problem statement goes as follows. Sushi has a sequence of integers a1, a2 up to an, and it is known that each element in this sequence is in the range 1, 10 to the power 6 inclusive. But the thing is that we don't know this sequence and we wish to find this sequence by asking some queries to the code. It is given that we can ask maximum 2222 queries, and in these many queries we have to find this sequence. So what does the query return? So first of all, the format of the query is as follows. We can ask a query of the format k comma x, that is give two integers k and x to the code. And what does the code do? The code does the following thing. It takes the integer x and inserts it in such a position such that if we remove that element, we get the original sequence. So, for example, if the original sequence was 3, 3, 2, 5, and 2, and we wish to query 3, 1. So what will be the new sequence? The new sequence will contain n plus 1 elements, that is this element 1 is inserted at position 3, and now we have a sequence of n plus 1 elements. And what does the interactor do is that creates this new array of n plus 1 elements and returns the total number of inversions in this array. So what do we mean by inversions? As stated in the question, the number of inversions is the number of pair in the given array, such that if index I is, let's say, less than index j, but the value at index I, that is here 3, if it is greater than the value at index j, then this counts as one inversion. So the interactor returns the total number of inversions after forming this new array. So we can ask a maximum of 2222 such queries, after each query we will be returning, the code will be returning us the number of inversions, and our task is to somehow use that information to find the original sequence of numbers, that is a1, a2 up to an. Further, the question states that the constraints are as follows. The size of the unknown array, that is capital N, can go maximum up to 100. That is, at the beginning of each test case, we will be given the value of integer n, that is the size of the array, and it can be maximum of 100. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. So let's begin with the approach to our solution. So initially, the whole array will be unknown to us. So let's say I denote the answer array by a sequence of zeros, that is unknown numbers, right? And this here in red uh, tells me the original array, okay, which is clearly unknown to us. So how do we find the elements of this array, whereas initially all the elements are unknown to us? So instead of randomly guessing some numbers or randomly querying, what we are going to do is find these elements in a sorted manner. That is, first we will find the smallest element. So what is the smallest element yet to be found? It is 1, right? So once we find the element 1, we will fix the positions. So we can clearly see that 1 will occur at two places over here. Now once we have fixed the position for 1, we will now use the queries to find the next smallest element that is yet to be found, which is 3, and then again we will fix the positions for that element. So here if I fix the positions for 3, so in the same manner, if I continue and go on finding the next smallest element and fixing the position, eventually we will be having the whole array. And so this right here is the final array which we will be printing as our answer. But the question is, how do we find these elements one by one, that too in sorted manner and in an efficient way? So let's see how we are going to do this. Let's say that the given array that we want to find is A, right? And we don't know the elements of this array, but there must be some number of inversions in this array as well, right? So if we want to query uh, such that the query returns us the number of inversions in the original array, what should be the query? So you can clearly see that if I query 1 comma 1, it will return me the number of inversions in the original array. Why? Because the original array will stay as it is, and 1 will be on position 1, and the only number of inversions will be from this part. Why? Because all elements in this original array are anyways greater than or equal to 1. So this adding this 1 does not contribute to any new inversions. So if we query 1 comma 1, the answer that we would be getting is nothing but the total inversions in the array. Note that I will be denoting the total inversions by this variable total underscore inv throughout the explanation of my solution and the code as well. So as discussed earlier, the approach or the solution to this problem can be divided into two broad steps. The first step includes finding the smallest unknown integer yet to be found along with its count. So initially we know that the answer array will be just a sequence of zeros, that is unknown integer. So we find the smallest element along with its count, and then the only step remains is step 2, that is finding the positions for this element in the answer array. So for example, if we find that the smallest element yet to be found is, let's say, 2, and it appears 3 times in my array. So I have to now find the 3 positions for the element 2 in my array. And if, let's say, the positions come out to be these, then I will fix the element 2 over here, and I will continue with my process. So focusing on step number 1, if we need to find the elements in sorted order, we need to make an observations on the queries of the type 1, x. That is, always the queried element x is put at the position 1. So what can be the possible queries? The possible queries can be 1, 1, 1, 2, 1, 3, and so on. So what is the trend or the sequence that is obtained after querying these pairs? So we need to make an observation on that. So to help with it, let's take a small example. So in this example, the original array which is initially unknown to us is, let's say, 3, 3, 2, 5, 2. So if we query 1, 1, we know that this will give us the total number of inversions in the original array. So if we calculate the total number of inversion, it comes out to be 5, right? But what if we query 1, 2? That is, here the query is of the type 1, x, where x value is 2. So If we query 1, 2, the number of inversions would still remain 5. And if we query with x value as 3, the number of inversions would increase to 7. And I have pre-computed the values for each of these. Let me just write them down. So as you can see that when I query 1 comma x and the value of x is gradually increasing from 1 up to uh, some big number, you can see that the answer that I am getting from the interactor is also increasing. That is, the number of inversions are also increasing. And that is what the observation you need to make. And this observation is going to help us focus on our step number 1 in finding the unknown elements in sorted order. So in this example, you can observe that whenever the value of query 1 comma x is changing, for example, when it is changing from 5 to 7 or 7 to 9 or 9 to 10, at the same time, the values of x, that is 2, 3 and 5, are nothing but the elements of our original array. So if you carefully observe the difference of these queries, that is 7 minus 5, that is 2, 9 minus 7, that is 2, and 10 minus 9, that is 1, is nothing but the frequency of the elements. So using these queries, we can easily find the element along with its frequency. So 2 occurs 2 times in our array. Then the element 3 occurs again 2 times in our array. And then the element 5 occurs 1 time in our array. And also, what is the range for this x? The x can range from 1 to 10 to the power 6, because it is given in the question that the array elements can only range from 1 to 10 to the power 6. But we cannot query all these numbers from 1 to 10 to the power 6, right? Because if we query these many times to find just one smallest unknown number, so the complexity would be too high, right? Because there can be maximum 100 elements, and if for each element we query 10 to the power 6 times, it would take too many queries. So we have to find an efficient way. So here comes the concept of binary search. So let's see how binary search will help us achieve this in less number of queries. First, let's define an variable known as last, which will initially be equal to our total number of inversions in the array. So if we define this variable last as total underscore inv, we know that the value of total inversions is 5, because 5 is the number of inversions in our original array. So we need to find the query x for which the answer is just greater than last. So we can observe here that 7 is just greater than 5. So we need to find this position so that we know that the value x minus 1, that is 2, here 2 is the value of our element. So we'll also be having a variable known as element, and we'll also be having a variable known as frequency. So using binary search on the range 1 to 10 to the power 6, we can easily find the smallest element for which the query just exceeds our last variable. And once we find that the corresponding value of x is, let's say, 3, then the value x minus 1, that is 2, is nothing but the value of our element, and the value of query, that is, let's say, res minus the value of last, is nothing but the frequency of the same element in our array. So with binary search, we can easily find the element as well as its frequency in the array. So this is how the binary search function is going to look like. So initially, the values of variable L and R will be 1 and 10 to the power 6 respectively. And we'll also be needing a variable known as mid. and also there will be a variable known as element which will be initialized to 10 to the power 6, but our binary search function will be responsible for calculating the smallest unknown element yet to be found. So what it will do is uh, recursively or iteratively it will calculate the value of mid and it will query 1 comma mid, and if this value is greater than last, it means that we have to go to the left. That is, our if our initial search space was, let's say, 1 to 10 to the power 6 and mid occurs over here, and our res is greater than last, then we reduce our search space to this and we ignore this remaining right half. So in this way we reduce down our search space each time by half, and at the end we reach our final position, that is uh, where the value of query 1 comma mid is just greater than the value of last, and at that position the value of mid minus 1 is nothing but our element. So here you can see that I have written element is equals to mid minus 1 at all times when res is greater than last. So finally when my while loop is over, I have the value of element in the variable elem, and the frequency for the same element is given by inv minus last. So in this way I have both the element as well as its frequency in the original array. So now in step 2, the only task remains is to find the frequency many positions of element in the answer array. So we have already calculated the values of these two variables. Now we only need to find these many number of positions in the answer array for this element. So how are we going to do that? Again, we will be using binary search to find the positions in an efficient manner. And as there are FREQ many number of positions, we will be applying binary search many times, and each time we will be getting one position. Let's see how to do it. So the binary search this time will be on the range 1 comma n, because these are the indices possible for the element. So let's say at some point of time our query is something like mid comma element, that is at mid index of our binary search we are querying the element. So the state of this query would look something like this. So this is how the array will look like if we query mid comma element, that is element will be inserted at that index mid, and over here the stars represent the elements that are already known to us, because we are assuming that this query is at some particular state. So let's say some elements are already known to us beforehand, so these are represented by stars, and the unknown elements are represented by zeros. So if we query mid comma element, the result, that is query of mid comma element, will be nothing but the total inversions in our original array, that is excluding element, plus the inversions caused by inserting element. Right. So after inserting this element at this position, some extra number of inversions would be caused. So they can again be divided into two categories. So they will occur only due to two possibilities. One, that is if there are greater than ELEM elements present on the left hand side, then these can cause inversions, and also if there are elements less than ELEM on the right hand side of position mid, then they can also cause inversions. So these two possibilities contribute to these new inversions that are produced due to addition of this element, and the other is the total inversions already present in our original array. So in reality, we know that the element ELEM can occur only at these positions because these are unknown till now. So the position denoted by zeros are the probable positions for ELEM. But if I assume that this position, that is mid, is such is present in such a way that all the actual positions of ELEM are present to the right of mid, then it means that all the zeros present on the left of mid are nothing but the elements that are greater than ELEM. Why? Because the other elements are already known to us and they are always less than or equals to ELEM. So we can clearly say that if mid is such a position that all the actual positions of our element are present to the right, then all the zeros present to the left of mid are nothing but the elements that are greater than ELEM. So we now can formulate a condition to steer our binary search according to our needs. So as we want to calculate the next position at which the element ELEM would occur, we can formulate the condition as follows. We will calculate the value of res minus left 0, that is the count of zeros present to the left of mid, plus total inversions, that is the total number of inversions present in the original array, plus right small, that is the elements present to the right of mid but are actually smaller than ELEM itself. So if we add these three variables and subtract it from res, the whatever value we will be getting, if that value is 0, it means that mid position is present on the left of all the actual positions of element, or if not, then we have to take mid more towards left. So now we have a steering condition. So we will always check the value of this formula, and if that value is equals to 0, then whatever is the current mid is a probable position for element. So we store that position in the variable known as pos, and at the same time we reduce our search space by half. So let's say if mid was occurring here and the formula gives the answer as 0, so we will ignore the first half and keep only the second half as our probable search space. That is, we will do L equals to mid plus 1. Or else, if this condition is not true, that is, if this formula gives the value not equals to 0, then we will just do r equals to mid minus 1, so that we move our variable mid to more towards the left side. And finally, when the binary search is over, we will assign ARR of pos is equals to element, and that's it. One binary search leads us to finding one position of the element. So this whole process of applying binary search or for finding position, we have to apply this frequency number of times so that we find all the positions for element, and then we can continue for finding our next smallest element. So once this whole process is done, at the end we change our variable last to INV. Why? Because remember that initially the total number of inversions were 5, and we were finding a position for which the inversions would be just greater than 5. That is, it was, like I remember, 7. Now we have to find inversions that are just greater than 7. So we have to update our last inversion count. So our last inversion count will be our 7, so that when we have our new inversion count, that is 9, 9 is just greater than 7, as discussed in the example in the very beginning of our solution. So in this way, we can find all the elements in sorted manner and all the positions for those elements as well, one by one, using binary search concept. Needless to say, the complexity of our algorithm is quite simple now to calculate. We know that for finding each element, we are applying binary search on the range 1, 10 to the power 6. So the complexity would be 100 into log 10 to the power 6, and for each of these positions in the array, we are applying binary search on the length of the array. uh, so that would be 100 into log 100. Why? Because the size of the array can be maximum 100. So if you calculate this value comes out to be around 2700. But it was given in the question that we can ask a maximum of only 2222 queries. So how are we going to achieve this? Remember that you can always store the answers of the asked queries so that if the same query is required again, you don't have to ask it again and you can use the stored value for your use. So if we memorize the answers or the query answers so that we can later use them, it will reduce the number of queries to less than or equals to 2222. For the detailed proof of this concept, you can refer the text editorial at the link given in the description. I hope you guys have understood my solution. If you want to master competitive programming while learning from world-class programmers, which include ICPC World Finalists, IOI medalists, and some top-rated programmers from the world, make sure to get our subscription on Unacademy Plus. We have live classes, recorded sessions, practice problems, as well as doubt clearance on Unacademy. Also, don't forget to use my referral code DarshanKool25 for instant 10% discount. The pseudocode for the problem goes as follows. First, we will be creating two functions, query and init, to help us get the answer for the query and to clear things respectively for each test case. Now, for each test case, we first start by taking the input for n and create an answer array which is initially filled with zeros. Now we calculate the total inversions in the original array by querying 1, 1 and storing the answer in a variable known as total underscore inv. Further, we initialize the variable last with total inversions as discussed in the solution. Now, until and unless we are able to find the smallest unknown element, we apply binary search to find that element, and if that element is comes out to be 10 to the power 6, it means that it is the last element and we set all the unknown elements to 10 to the power 6 and break from the loop. Or else we know that we have to fix frequency many positions for element in our array. So first we calculate the variable frequency and that many number of times we apply binary search on our array length to fix one by one the position for element. And once we are done doing all this, before starting the whole process again, we update the value of last because we want to now find the next smallest element. And once the whole this while loop is done, we report the answer and continue with the next test case. Remember that before starting each test case, we have to clear our stored previous query answers. So we will be making use of the function init over there. So this part will be more clear when we see the code. So let's quickly go through the C++ code for the problem. So as stated in the pseudocode, we have created two functions, query and init, to help us, right? So the query function takes two parameters k and x, and if the answer for k comma x already exists in the created map, it returns the answer, or else it asks the query and then stores the answer in the map and returns the same. Also, the init function is just responsible to clear out the map before starting each new test case. I have created a variable count so that I keep a track of total number of queries that I am asking to the interactor. If the count at all exceeds 2222, my code will stop there itself. Coming to the main function, for each test case, we start by calling the function init to clear out things. Then we take the input for n and create an answer array which is initialized with 0 values. Then we calculate the total inversions by querying 1, 1 and initialize the last variable as discussed in the solution. Now, our first task is to find the smallest unknown element yet to be found. So that can be done using binary search, and if that element is comes out to be 10 to the power 6, that is in my code capital M, then all the unknown elements uh, remaining are 10 to the power 6. So we just set them as 10 to the power 6 and break out from our original loop. But if that element is not 10 to the power 6, then we have to fix frequency number of positions in our array for the element ELEM. So we do that by applying binary search frequency number of times. So each time we start with L is equals to 1 and R is equals to N, which is the size of the array. And at each step we calculate res, which is found by querying mid comma element, and then we calculate three variables: left 0, right small, and total inversions, which is already known. And if this formula gives the answer as 0, it means that mid is on the left of all remaining positions for element. So we store the value of mid in pos and shift our mid towards right by doing L is equals to mid plus 1, or else we have to shift our mid or position towards left. So we do that by doing R is equals to mid minus 1. Finally, when the binary search stops, we fix the position with the value element. So answer of pos is equals to element, and this whole step needs to be done frequency number of times. Once we are done fixing all the positions for the current element, before starting the whole process again, we fix the value for last as inversions, because now we want to find the next smallest element. And finally, when the outer while loop is done, we report the answer, and that's it. We are done with the solution.